Hi, I'm Greg Sullivan from Dover Microsystems. This presentation was prepared in collaboration with Steve Milburn, our Chief Technical Officer. I'm going to start by giving an overview of the increasingly large set of intrinsic security features in the RISC-V ecosystem. And then I'm going to back up a little bit and consider common elements that of all of these security features, such as metadata, flow of metadata, checking of metadata, and make an argument that rather than implement all of these features separately with their own implementations, their own notions of metadata and checking, that there's some sort of commonality, that common architecture that we could employ to avoid over complex hardware implementations and software tool chains for that matter. I'll take a short detour into some theory, reviewing Fred Schneider's execution monitoring and security automata work from the early 2000s, which categorized the class of policies that can be enforced strictly at runtime, which is, of course, what an instruction set would be doing. I'll refer back to some even older history from the early days of computers and the DoD Orange Book in an attempt to formalize what a secure machine would be, and calling for some basic mechanisms that I think we should look to as a guide to implementing core security features for RISC-V. Finally, I review the trade-offs between hardware and software, look at some specific features that we've encountered in our own work that we recommend avoiding, and also recommend some general principles for implementing a complete set of security features. This graphic was presented by the Security Horizontal Committee chairs during the meeting in November, and is an attempt to pull together all of the intrinsic security, that is hardware-based security features currently being considered or already ratified in the RISC-V ecosystem. I'm going to focus on a subset of these features for this talk. First of all, you'll notice, of course, that all these features I've highlighted implement some notion of confidentiality and integrity, which is, of course, what you'd expect, because that is really what the definition of information security is. Cryptographic features, however, are really focused on confidentiality and integrity of data at rest or in transit. And I'm going to be focusing for the rest of this talk on what's called execution monitoring, which is the runtime enforcement of security policies at the instruction level. And that leaves these two classes, and I'm going to review briefly some of these features because I realize not everybody is familiar with all the acronyms. In the box labeled robustness here, we have CFI, control flow integrity, and BTI, branch target identification, which are focused on control flow integrity, that is enforcing adherence to some notion of a control flow graph. That's what these features, at least under consideration, are focused on. Then we have memory safety, pointer safety and memory tagging, which are fine-grained memory safety when it's a pointer safety and the pointer is a function pointer. Obviously, that's related to control flow integrity. Otherwise, it's fine-grained memory safety with respect to some runtime notion of allocation. And then we have capability extensions such as the Cherry architecture, which I will discuss more later. Then over here in what's called trusted execution environments, which I generally call compartmentalization approaches to security, we have coarse-grained confidentiality and integrity. I call these coarse-grained because they really draw a box around large regions of memory and instructions and guarantee that one compartment, instructions in one compartment, can't violate the confidentiality and integrity of data in another compartment and vice versa, but they don't guarantee the confidentiality and integrity of the data within the compartment. So there still may be buffer overflows and so forth within a given compartment, but the scheme adds work factor to an attacker where they might have to compromise multiple compartments to reach their final goal. I forgot to mention that the robustness category here, I call indirect confidentiality and integrity, because memory safety with respect to memory allocation is certainly related to confidentiality and integrity, but is an approximation of what an application notion of confidentiality and integrity is. For example, you can obviously violate confidentiality by simply writing a private value to a public output without using a buffer overflow in the process. And likewise, a buffer overflow may overwrite data that is, for instance, not used and therefore wouldn't violate application level notions of confidentiality and integrity, which is not in any way to say that memory safety is not a very important feature to try to enforce. Furthermore, control flow integrity type features also aren't directly supporting application integrity and confidentiality, but nonetheless, it's assumed important to enforce control flow integrity if possible in order to avoid violations of application level confidentiality and integrity. So what I'm going to do for the rest of this talk, much of the talk, is to point out common features that are common across all of these different feature implementations. Obviously, they all focus on some notion of confidentiality and integrity, which is really the definition of information security. There's going to be some setup and initialization of these policies at boot time or application load time. It's going to be some instruction level checking, whether it's due to new instructions added to the applications that are specific to security functions, or maybe the microcode of instruction implementations has been updated to also check security features. And finally, and the primary goal of the next couple slides is focusing on metadata, which needs to be maintained for all of these features. So for example, the control flow integrity type features for forward edge control flow integrity, that is checking whether a jump or call should be allowed, you're going to want to have some metadata associated possibly with the target instruction, namely from what source locations it is allowed to be reached. This is sometimes called a come from list or ID. Target instruction might simply say it is a legal target instruction, and that by itself is a very coarse-grained notion of control flow integrity. Similarly, the instructions that are doing the control transfers themselves might limit the number of the set of targets they can reach by identifying some sort of ID, target ID. And furthermore, many of these implementations maintain a contextual metadata, that is whether the chip, the instruction stream is in the process of jumping or not. For backward edge control flow integrity, that is preventing return-oriented programming and the like, where the attacker takes over the call stack, you certainly want to know whether an instruction is a return instruction or not. And if you encounter a bit string, for instance, in stack memory, it might be important to know whether this is a return address. And furthermore, if it is a return address, maybe you want to check whether the instruction accessing this address, maybe overriding or dereferencing, is a privileged instruction, for instance, an instruction in a function prologue or epilogue. Finally, I don't think there's a particular working group focusing on code pointer integrity, but it's another popular control flow integrity approach where the any individual words in memory that are used as function pointers or code pointers for indirect jumps are labeled as such and therefore prevented from being inappropriately modified. And the fact whether a bit string is a function pointer, that metadata should flow along with that value if the value is stored or read from memory, moved around from in registers and so forth. So there's some notion of metadata flow involved. For memory tagging security features, A couple of some of the discussions going on are looking at the same approach as ARM memory tagging extensions or the Spark ADI feature set, where there's 16 different IDs, we call them colors, where every pointer at allocation time, the returned pointer is given a color, and all the words in the region that's just newly allocated are given the same color. And thereafter, any pointer operations, there's a check to see whether the pointer color matches the memory region color. So the metadata is maintained both on the pointer and with respect to words in memory. And when pointers themselves move around memory to register and are maybe modified, the fact that they're a pointer and the region to which they're allowed to point should flow with them. Words in memory, the region that a word is in memory does not flow to registers, it sticks with the memory location. For capability type approaches, such as Cherry, there is some metadata, or even you could call it meta-metadata, which is whether a particular bit string in memory is a capability or not. If it is a capability, then it must be protected from arbitrary modification or reference. But the capabilities themselves, in a sense, carry around their own metadata. A capability is some sort of data structure that within it contains information such as whether it's a pointer to memory, and if so, what are the base and bounds of memory, and maybe other access rights associated with this capability. So the capabilities sort of flow as first-class objects themselves, but obviously there has to be software support, the compiler support, and so forth to generate these, the initialization of and then the flow of capabilities. Finally, the wide range of compartmentalization approaches also have some notion of metadata. Typically, there's a current context that's tracked, and specific ranges of instructions in memory might have metadata, that is, which compartments they're associated with, and pointers, which compartments they can dereference. So a quick detour into some theory. Back a few decades ago, Fred Schneider and company at Cornell tried to characterize the class of security policies that can be enforced purely dynamically, which is of interest to us as we're looking at an instruction set, because that's what instruction sets do. That's what CPUs do. They operate purely dynamically. So he characterized the set of so-called execution monitors and came up with a formal representation of execution monitors in terms of finite state automata called security automata, a trivial example of which is on the right here. Now, these automata can get quite bulky and are probably not used by any actual systems to both specify and enforce security policies, but they're useful from a formal perspective. There are common software techniques for enforcing what turns out to be the equivalent to execution monitors, and these are typically called inline reference monitors, IRMs. An inline reference monitor software approach, adds instructions to an application, whether it's binary rewriting or source code rewriting. And these instructions precede security relevant operations such as memory accesses or calls, and check against metadata maintained on the side whether or not these operations are allowed. So obviously, if you're inserting instructions in line with the application code, you're having a serious detrimental effect on application performance. And so these aren't typically deployed. One class of inline reference monitors that's worth a note, though, is what's called software fault isolation, SFI, from Robert Wabi and company. And at least they initially described it. And this is a use of inline reference monitors such that you can do very fine-grained compartmentalization, arbitrarily fine-grained, and you insert checks whenever there's a jump or a memory reference to enforce these compartmentalization. But what you avoid is heavyweight context switches, such as you need for virtual memory context switches or similar approaches. And they show that actually avoiding these heavyweight context switches by doing sort of fine-grained checking actually can improve performance when you have lots of compartments. Also, our inline reference monitors have been used for fine-grained memory safety, control flow integrity, and so forth. A well-known inline reference monitor is address sanitizer and other sanitizer plugins for the LLVM compiler framework. These are widely used during at least the testing phases of software development, but are typically not deployed because of the high performance overhead I mentioned earlier. Now, as we at Dover have been trying to implement our own version of execution monitors over the last few years, some acquaintances pointed out that, well, actually, quite a long time ago in the 80s, there was this orange book produced by the Department of Defense, which is actually a predecessor to the common criteria, which many of us encounter nowadays. But they laid out these fundamental ideas of what it means to protect a system. And they included terms such as reference monitor, which we just talked about. But they didn't say it was necessarily a software construct, but just generally some abstract machine that mediates all accesses to objects by subjects. And at the instruction set level, an object is a word in memory or a register, and a subject, the object is a word in memory or a register, subject is an instruction. Also, they mentioned labels, which is what I've been referring to as metadata, that give access and other security relevant metadata associated with the objects, that is the words in memory and registers of a system. And then the Orange Book goes to great length to point out the obvious fact that this metadata, as well as the logic of the reference monitor itself, must be protected from assumed malicious code in the application. So the question is, first of all, are there some lessons learned from this, both the formal theory and also the original ideas for what it means to secure a system? Furthermore, when we are creating all these individual features for hardware security, are there any general and reusable architectural features that can support multiple of these execution monitors? Also, and therefore, what should we incorporate really in all of our RISC-V designs? And also whether there's a mix of hardware and software for implementation of these security features. So to review the original figure that I showed from the beginning that was presented at the Security HC meeting, all of these features, including cryptography for that matter, could be done in software via IRMs, or as being currently pursued, be done in hardware. So if we were to envision how to support a range of execution monitors in hardware, where each of them maintains their own metadata, does their own specific sorts of checking and updates, and so forth, what might we come up with? And this is a notional idea to sort of get the conversation started. On the right here, in the lower half of the CPU box, is in purple is this standard execution pipeline of a CPU. There's some instruction decode, possibly a request from memory. Later, when the memory value, if any, is available, and the register values, we get to the ALU control and so forth, and other logic, possibly resulting in some updates to registers and memory. Well, maybe we want a parallel pipeline for monitoring, where there's some notion of decode, so the monitor knows what sort of instruction we're talking about, where there's a register file of application values in the CPU execution pipeline. There's a register file of tags, that is binary encoding of metadata, in the monitoring pipeline. Similarly, and very importantly, when there's a request, let's say to an MMU, and there's a mapping from virtual address to physical address, there ought to also be a mapping to tag address. And when there are and as values are maintained in caches, it should be an invariant that for every value in a cache, any tags associated with that value must also be in the cache. Now, this doesn't mean that this doesn't imply that tags and values need to be the same size. In fact, typically tags would be much smaller than the values that they're modifying. All that means is you can fit a lot more tags in a single cache line than values. And so, but the key point is that when a value is produced for the execution pipeline, the corresponding tag or tags should be produced for the monitoring pipeline. Finally, in the monitoring pipeline, where it says checks and flow, that's really where all of the security feature specific logic would reside, whether it's control flow integrity, memory safety, compartmentalization, and so forth. So hardware, a quick survey, hardware has the benefits of being fast and harder to subvert. But I want to point out that every time you add a new feature, you're complicating the ISA, you're having serious impact on tool chains, that is compilers and possibly secure boot and the rest of it. So there's a cost, a cumulative cost, and maybe a compounding cost to adding hardware features. Software has the reverse set of attributes, right? There's no impact on the instruction set and universally flexible. However, can be a huge performance impact, and possibly in the worst case, you're actually adding to the attack surface of applications. So finally, we get to do's and don'ts, the promised do's and don'ts. And I'm going to start with the sort of fine-grained lessons learned that we've run into at Dover over the years with different architectures, adding clever performance features that make the job of monitoring for security much harder than they should. In the RISC-V world, for example, when there's exception delegation, we have to figure out where the exception PC was stored, and it's not obvious because it may be, you may wind up on an instruction in a different mode than where the exception was thrown. Similarly, in some architectures, there are multi-word load and store operations, for instance, when you're loading and storing registers to and from the stack. And this seems like a good idea, but it makes the job of figuring out what memory operations are happening obviously harder. And when these multi-word operations can be paused or canceled, and then maybe resume or maybe not, it makes the job of trying to keep track of what memory is being updated harder and harder. Then even more difficult is the notion of lazy register spills. Some architectures had the clever idea that, well, we don't really need to save the register to the stack until it's actually overwritten. And so what can happen is when a register is overwritten, suddenly there's memory traffic to a stack, and this is very hard to figure out why that's happening. In the interest of time, I'll skip the next two, but register windows are another clever idea that makes decoding instructions very, very hard. So the final high-level set of guiding principles for designing for a large and increasing number of security features, hardware-supported security features, is we just can't keep adding instructions and CSRs for every desirable security feature. This will be what I call death by 1,000 features. It's a verification nightmare. It keeps making the software tool chain more and more complicated, and will just make the architecture way too complicated. It won't be a RISC architecture at all anymore, and that we want to obviously avoid. On the other hand, we can't just use inline reference monitors, powerful as they are for everything, because this performance is extremely bad. And lastly, please don't decide to just steal bits for metadata when you think that they're not being used elsewhere. This was the approach taken by ARM-MTE and I think Spark ADI. They decided, oh, well, there's these 4 upper bits of pointers that nobody else is using. Well, we'll use them for metadata. And this is both insecure, because now these bits are really in the realm untrusted application code. It's irregular because not every feature can find a few more bits to steal. And it doesn't scale for the same reason. It's really a classic case of security being a second-class citizen. And we really have to, right up front, allocate memory and logic and gates to storing, checking, and maintaining metadata. So what to do is to embrace metadata, assume every element of the SoC has metadata. We still need a hardware root of trust, and we want to have a common monitor interface, and we want to make sure we have this metadata tracked and checked for all memory initiators, not just the CPU. And that's it. Thank you very much.